All right. Let's go ahead and get started. For those of you joining on Zoom, I don't know why the camera keeps zooming out like it does. Hopefully it stays as it is. So today the new material we're really covering isn't too much. I am going to be talking a little bit about vectors, a little bit about math, but should be more or less a refresher. But the new material today, the new material we're going over today is understanding this concept of resistivity. So we've talked about resistance, right? We said resistance is like this thing for preventing charges from flowing through a circuit, right? Measured in ohms and all this other stuff. But what exactly goes into resistance? Some of you guys may have seen resistors in your past, and we've talked about resistors, but what exactly is a resistor and how does one go about making one? Well, resistivity is the answer to all of our questions. And it tells us that the resistance of some material, the amount of resistance it has depends on two things. It depends on what material are we trying to make charges flow through. Because it depends on material, we call this a material property. Resistivity is a material property. And different materials allows charges to flow better or worse than other materials, right? This gives us this idea of conductors and of insulators, right? If we try and flow charges through aluminum, that's relatively easy. But if we try and make charge flow through a plastic, that's more difficult. So that's where this idea of resistivity being a material property is. It all depends on what it is we're building it out of. All materials of the same type have the same resistance. So same resistance, or sorry, same resistivity. Represent resistivity with the Greek symbol rho. So I'm going to be using that as shorthand for a while. Same rho or same material. Now, how does this help us when it comes to resistance? The thing we've been talking about for a couple of weeks now. Well, something that has more resistivity will generally give us a resistor of higher resistance, right? Something that is harder to flow charges through will become a better resistor. So how do we relate this to resistance? Well, resistance depends on this resistivity, right? We expect more resistivity means more resistance, so we're going to put equal to rho, right? We double the resistivity, we're going to double the resistance. So we're building our capacitor. Mine is elsewhere right now. If we're building our resistor, we determine what material are we building this resistor out of. That determines the resistivity. Also depends on a couple other things. If our material, if our resistor was longer, and I'll explain why this is the case, then it's more resistant. So it's going to depend on the length of material we're using to make our resistor. All this will come together in a second. And it depends inversely on how wide our material is. So we call this cross-sectional area A. This is the relationship between resistance and resistivity. Now, give you a more concrete understanding. We're building a resistor, right? A resistor is nothing more than a long strip of wire coiled up so that you can fit it in a nice small package, but it's nothing but a long strip of wire. So we draw out our wire, right? This long strip of wire. We apply a potential to it. We say, all right, we're going to hook up this side to the battery and hook the other side up to the other side of this long wire. We want to know how hard is it for a charge to flow through this material. We want to know how hard it is for a charge to flow through this material because that's what resistance is. How hard is it to get through it? If we use a plastic, it's a lot harder to push charges through, right? You hook up a battery to a piece of plastic, it's not going to give you a current. So higher resistivity means higher resistance. Higher resistivity means plastic. Also depends on the length. And the common analogy I like to give at this point is we think about our commutes to school, right? It's a lot harder to get somewhere quickly. It's a long travel distance, right? So we increase the travel distance, we increase the length, we increase the difficulty it is to get to where we want to go, increase resistance. Does that make sense? Any questions? Yes. A, I'm about to get to that. So A is our cross-sectional area. Again, using this analogy of our commute here to school, we think about the roads that we take. If roads, it's like a one-lane road, it's going to travel slower, right? But if we're on like a 4-lane highway, then we're going to travel quicker, meaning that the more space we have to spread out, the faster we'll generally get through, meaning we increase the number of lanes, we decrease the resistance. In this case, the lanes, we're saying how close together are these electrons going to be as they flow through. If they have to go through single file, it's going to take them a lot longer if they can spread out and go through. So literally what A is it's the cross-sectional area of this wire. We give our electrons more room to go, then they're going to spread out and be able to flow through quicker and lessen the resistance. So A is the cross-sectional area. And for a cylindrical wire, which is what we'll be assuming today, how do we calculate the cross-sectional area of a cylindrical wire? The radius. What about, not volume, area? What about the radius? Someone said radius. It does depend on that. pi r squared, right? It's just a circle, a cylindrical object. Its cross-sectional area is the area of the circle,
Oh,
right? Pi r squared. P squared over 4 is the way I like to think about it, because oftentimes when you deal with wires, you're not given a wire's radius, you're usually given its diameter. So sometimes it's more convenient to use d squared over 4 rather than pi r squared, but that's just an easy relationship, right? Radius is half of the diameter.
oh, so you put diameter over. Oh.
Yeah. D is your diameter of a wire. So all of this is to just say that if you want to build a resistor, which is something we often want to do when we're dealing with electronics, not necessarily build it, but choose a resistor, a specific value. But if you want to build a resistor, you got to pick a material, and you want to pick a material that's suitable enough to get charges to flow, right? You don't want too high of a resistance, but you pick the material. The material tells you what rho is. You know, do we choose aluminum? Aluminum has a specific value for this. We choose how long do we want this wire to be, and what is the thickness going to be. And that's how resistors are made, is you just pick the values that you want to use to get the specific value of resistance. This is the equation that determines resistance of the material. And once you have that resistance, you go back to doing Ohm's law. You attach this wire to some potential difference, and what happens? You get a current flowing through it according to V equals IR, Ohm's law. What happens after that? Well, your circuit behaves in whatever way you built it to behave. But this right here is a relationship between resistance and what's going on inside the actual resistor that you're building. Are there any questions about this? Thoughts, comments, concerns? Yes.
Another question for this. I can't see well under the sign D under
Four?
Oh, I thought it was mu.
No, that's any better. Any other questions? Thoughts, comments, concerns? All right. Now, there's one thing that I really want to cover with you guys. And I'm going to cover it more in depth, like 15 minutes before the class ends. But for right now, for the time being, I want to remind us about vectors, right? We've dealt with vectors before. Vectors, we need to describe them somehow, right? Usually when we have a vector, some directionality with some magnitude associated. Right? Say magnitude and direction defines our vector, yes? So we can do this two ways. We can say, all right, this vector right here has some magnitude equal to its length at some angle theta. So we say our force vector F has a magnitude. What is that magnitude? Well, if we're dealing with Coulomb's law, magnitude is K Q1, Q2 over R squared. If we want just the magnitude, we take the absolute value. Right? Last week when you did the classwork, you should have found some angle theta based on the directionality of where the charges are located. So we say that our vector F has magnitude this, and its direction is theta degrees above x, right? Of positive x, because that's where we're measuring our reference. This is one way to do it, magnitude and direction. But the other way to do it, and this is usually a little bit more convenient when you're going to start doing math with this, is we take this vector and we break it into components, right? We say this is our x component, this is fx, this is fy. So we break our vector into components. Do you remember how to do this? Are there any questions about that? We're good with this? Someone's getting a call? What's up? Can we go through it? Absolutely. So we look right here. We see that our vector, our magnitude, and its two components form a right triangle. This is always going to be the case. The two legs meet at the 90 degree. Always. For any vector, its two components are always going to be 90 degrees to each other. So how do we figure out the relationship? Well, now we use sines and cosines. We say theta, opposite to theta, the opposite leg is going to be Fy. The adjacent leg is Fx. So when we look at sine of theta tells us what? Tells us-
Y over radius, the radius, whatever.
Opposite over hypotenuse, right? Opposite is going to be Fy over the magnitude F, the hypotenuse. You use cosine. Cosine theta is equal to Fx over x, over the total force, the magnitude of the force. But we have to be careful because these formula work only under the condition that theta is measured with respect to the x-axis. If you measure it with respect to the y-axis, then what are we looking at? If you measure it with respect to the y-axis, we're looking at that angle. Suddenly, what was opposite is now adjacent. What is adjacent is now opposite. So if you measure theta with respect to the y-axis, then you have to flip your cosines and sines. Still just using trig, and this is why it's useful more often than not to just draw out your triangle instead of relying on formula. Understand where these formula come from, not just trying to plug and shove. But once you have this x and the y components, I know,
That's it.
make it more obvious x and y. But once you have your x and your y component, then we can denote vectors a different way rather than saying magnitude with some angle. Instead of this, you can use component form to represent our vectors, right? We can say our vector f, our full vector notation, we say is equal to the x components I hat plus the y components j hat. And why is this useful? Well, why this is useful to represent it in this notation is because let's say this is some vector f1, right? 1, x1, y1. This is all just one force vector, but we have another force vector to deal with. Let's say we have some force vector f2, which is equal to fx2. Right, we have two force vectors. When we want to add these together, how do we add these together? We add them component by component. We add these two together. Then we add these two together. And the addition of these two give you your net x component. The addition of the two y components give you your net y component. When you're dealing with vectors, you have to add vectors component by component. Very important, very important. Today you're going to be dealing with a problem. One of the problems deals with having three forces now acting on an object. We're going to add those three forces together. We need to be sure to consider adding them component by component. Now, when you do this problem, try and attempt it. Towards the end of class, I am going to start the solution with you guys. I'm going to work through it. I'm going to give you guys sort of my thought process when approaching these problems. So it's worth sticking around towards the end of lecture, but I'm going to wait till the end of lecture to start that because I do want you guys still to struggle a little bit with it. I want you guys to have that initial difficulty so that when you see the solution, you see something clearing up in your mind rather than just passively looking at me solve something. Does that sound all right?
Yeah.
Any questions, any thoughts, comments, concerns? You good? Okay. Let me go ahead and put on the board your you guys should notice as the weeks go on that these problems are getting a little bit more and more difficult. That's the idea. So if you find yourself struggling, I want to emphasize that please, please, please ask for help. You know, there's no shame in ever asking for help. We're here to assist you. So be sure to raise your hand, be sure to ask for any clarification. There's no question too small, no question too simple. We are here to assist you. For those of you on Zoom, I'm gonna put on Canvas. Give me a moment. Get it on Canvas. Can you guys make sure that like around 7:30? Yes. All right, for those of you on Zoom, it should be linked in the Canvas page and get it pasted in the chats. Okay.
So you guys are. You guys are both gonna be on Tuesdays and one time. And we'll go to Thursday.
Yes.
You're still on those. Sound good?
Is it?
There's also been a couple of changes to room locations for your LA sessions. Zori is now going to be in 120 PS 123 upstairs for all of her sessions. So just be aware that those locations have changed and take note of them. I will make these. I will post these on the campus site as well.
What times of LA sessions ever change during the semester?
If we find that sessions are not getting attended, they will.
Oh, shoot.
But if they're getting high attendance, then
So it's still a thing,
yeah. All right, everybody. So I want to walk through as an example how to go about the process of solving problem 3. I'm not going to solve it in its entirety, but I am going to give you a pretty decent guide, pretty good place to start. If you have any questions, be sure to ask as soon as those questions come up, right? Don't sit on these questions. Feel free to interrupt me if I'm talking, just say, hey, I got a question over here. So this question asks you two things, right? Asks you about the acceleration of this proton, the acceleration of this electron, right? We're going to take it in steps. We're going to focus on one thing at a time. We're going to first focus on this top left proton. Now, when you solve problems, it's always a great place to start by labeling everything that you can, right? We're going to take this picture. We're going to label it as much as we can. One of the first things that I like to label is these particles. I'm going to say this is particle 1, 2, 3, and 4. This is just a nice, easy way to deal with subscripts that we're going to deal with later. The other things we might want to label, distances. We might want to label this 12 nanometer distance. Well, that is distance r between particles 1 and 2, r1, 2. We'll say 1, 2, 3, 4. Distance r1, 2 is that 12 nanometer distance, right? This is why numbering things often helps, because I look at this and I immediately know what r1, 2 is, right? Distance between 1 and 2. You could do a single subscript, that's perfectly fine, but you're going to have to keep track of what all these subscripts mean. I also might want to label R13 equals to 10 nanometers. We might look up a couple of values that we know we're going to need. What do you think we're going to need to solve this problem that we need to look up?
Proton charge and all
I need to know the charges of these things. Q1 and Q2 equal to each other, and what does that equal?
1.602.
Minus 19, what? Coulombs. Always include units. Q3 and 4. Same thing, but with negative. Yes, does that make sense? Just labeling our things, starting out with this initial step. Okay, what might we want to do next? Solving this problem, we look at it. We've labeled a lot of our knowns. what should we do? What do we think to do? Yes. We might want to know what the distance between 1 and 4 is, and we might want to know this because what concept are we applying here? We're applying Coulomb's law. Coulomb's law says F equals K Q over R squared. Each pair of charges has a distance. We have distance between 1, 2, we have distance 1, 3. Can be able to calculate that for us, no problem. But distance 1, 4, we do not have that. We don't have this distance. So we have this unknown value. We have R1, 1, 4. Big one question mark. No clue. Right? We know we're going to need this. What else are we going to need? We need mass eventually. Theta might be an interesting thing to look for. When we construct a triangle with these 3 charges, I'm just going to do this triangle over here. So I've already had it mostly completed. I have this triangle right there, right? It's a nice right triangle. We might want to figure out some angle, right? We might say theta or phi. One of those 2 angles might be important. It will be. That's another unknown. We don't know what that is. Maybe this question mark, phi is a question mark, angle, no idea what it is. We'll figure it out. What else might we care about here? Do we feel like this is a good starting place, maybe? So, okay, let's move forward, right? Start applying some of the knowledge that we have. What knowledge do we have? Well, one of the unknowns that we have are 1, 4. What are other unknowns we have? Well, we don't know what the forces are. That's what we're looking for. We don't know what acceleration is. Could have included that on our list. Well, let's just start with something we don't know. R1, 4. How do we figure that out? Diagram theorem. We got our nice right triangle where we have R1, 3 for this leg. R1, 2 is equal to R3, 4. So we have that leg as well. So we know that R1, 4. It's not quite an unknown. We have enough to calculate it. R1, 2 squared plus R1, 3 squared. Figure out what that value is. What is this value? Does anybody have an answer? We did something there without noticing it, though. What did we do without explicitly saying? We converted to meters. You should always think to do that. So looking back at these values, you should always think 12 times 10 to the minus 9 meters. 10 times 10 to the minus 9 meters. So when you're solving problems, best advice I can give you. Start by writing out things that you know. Start by converting everything to SI units. If you convert everything to SI units, you don't have to worry about it later. So do it immediately, get it out of the way, and then start applying equations, figure out some of your unknowns. Theta, how do we figure out what theta is? Sines and cosines, right? Trig functions. For theta, we have adjacent, we have opposite. We just calculated hypotenuse. So sine, cosine, tangent, all of these are available to you. Thing I will tell you is you'll get the least amount of rounding errors by using the values that are given. Right? The values are given are your legs, so use tangent. That being said, if you want to use your hypotenuse, you shouldn't get really that much of a rounding error. You do sine, cosine, yes.
So when you use sine,
Mhm. When you use sine and cosine, So it doesn't matter, but I'll say use SI units to be safe, because what you're doing is you're using, let's say, sine inverse, right? Sine inverse of what? What are the values we want? Sine tells you opposite over hypotenuse, right? So if you use 10 nanometers and that 15.6 nanometers cancel out. But I'm going to strongly recommend always convert things to SI units. Your 10 to the minus 9s are going to cancel out as well. But always convert to SI units. That's always the safest route. If you ever have a question, can I use nanometers or should I use meters? It's always safest to use meters, to use your SI units. Yeah, it's like any other SI prefix, right? You think of this nano, you think of this little n. This little n is exactly equal to times 10 to the minus 9. One-to-one replacement. You just erase that nano, put in 10 to the minus 9, you have your meters. So anytime you have nano, just put in that 10 to the minus 9. You'll notice I wrote 10 times 10 to the minus 9. I could have wrote 1 times 10 to the minus 8. I could have just written 10 to the minus 8. All equivalents. I prefer, my brain works best to see 10 nanometers though. That's the way my brain works. You could of course write 10 to the minus 8. Any other questions, thoughts, comments? So why is it important to know theta? Here's the crux of the part of the solution I want to point out to you guys. The reason why I'm looking specifically at this. Why do we want to know that angle theta? Well, the force between this proton and this electron, what direction is that pointing in? It's an attractive force, right? Be attracting downwards. Described by exactly the same angles that this right triangle we just constructed is. So you find this force. This force represented F1, 4, and again using these numbers as subscripts to know which one's which. You calculate the magnitude. How do you calculate the magnitude? Use Coulomb's law with the distance we just calculated. Q and Q being proton and electron. So we can calculate Coulomb's force. That's no problem. We know how to do that. We have the magnitude. We have the direction. So what are we going to do with this? You know, we find this force, we find this magnitude. We have these other two forces to deal with between proton and electron. But we have to add these together, right? Find the net force. Find the net force by breaking this F1, into its components. And you break it into components using this theta, right? You say F1, X components is equal to what? It's equal to F1, magnitude of the whole thing times your we'll say cosine theta because that's what we were looking at. That's why we want theta. If we used phi instead, we'd use sine phi. Both give you equivalent answers. You find the y components. 1, 4y. And it's going to be equal to 1, 4 times the sine. Cosine phi. Both will give you the same answer. So now we have the components of F1, force between 1 and 2. That's going to be entirely in the x direction. Entirely an x component force. F1, entirely in the vertical direction, entirely a y force. So at this point, we have all of the components. We add vectors. How? Mathematically, what do we do? Tip to tails geometrically. Algebraically, what do? We add component by component. Right? So when you're doing this problem, be sure be sure to add its component by components. Component by component. And once you have that, you have your net force. Acceleration is just net force over mass. In the second law. Is there anything here that isn't sitting well with you? Be sure to ask me as soon as possible. But if this all seems like it makes sense, if this is all relatively good for you, you're in a good spot. So, are there any questions, thoughts, comments, concerns? Okay, I will be here a little. Oh, sorry. Hmm? The Y component? Right here? Sine theta? Well, this one's cosine theta. The other one's sine theta. Right, because our angle theta is right here. The adjacent is going to be the Y component of your force. Adjacent is given by. Wait, did I mix that up? No, sorry. We're using theta. Theta is opposite is Y. Opposite is sine. So I think that works. Are there any other questions, thoughts, comments? Do you feel okay about this? All right, be sure to ask any questions that you have before you leave. Otherwise, we are getting pretty much towards the end of lecture. And I'll see you guys next time.